glad that you're here, and particularly looking forward to, I am, and I'm sure you are, to hearing the presentation today. Now, so what do these people have in common? What do you think? Pardon? Come on, Laura, you're a historian. What do they all have in common? That's right. They all died of tuberculosis. Now, these are just the famous ones. For every one of these, there are God knows how many millions of people who were living particularly after the Industrial Revolution, were living under the circumstances that lead to propagation of infection with tuberculosis. Crowding, I guess poor nutrition, poor ventilation, but mainly proximity. And somebody's got it, they sneeze a bit, cough, particularly cough, and before you know it, there's an epidemic. So these are the ones who usually attract attention. Oh, there's one other thing that's interesting about it. Of course, before Koch discovered the tubercle bacillus, and I guess somewhat afterwards, the disease itself repeatedly pops up in history and in literature. It's described in ancient times, mummies, and so forth and so on. But what I'm thinking about is there was sort of a romantic period. And I think George Sand probably contributed something to that, because her lover, Frederick Chopin, died of tuberculosis in her arms. And she commented that his cough was such a gentle, beautiful, she made a romantic thing out of it. And the designation, the White Plague, has two origins, apparently. One, it was first recognized epidemically, at least in the Western world, in Europe, and it was almost entirely amongst Caucasians, so that may have been the basis of it. But also there was this romantic notion that people who had tuberculosis sort of turned pale. And in the 19th century, in the 20th century even, young women, especially women, being slightly pale, that was considered to have certain admirable qualities. In the opera, it appears in Mimi, in La Bohème, and in the heroine of Verdi's La Traviata, and throughout literature. This was a good disease to have. Baloney, this was a miserable disease to have. This is a rarely acute, fulminating. It's almost always chronic, debilitating, and very painful. To die of respiratory failure is probably almost the worst kind of a death you can imagine. For many years, there was a huge argument about whether intestinal and respiratory disease, the lesion in the lung, whether they were the same. And the thing that seems to have changed the whole balance was pasteurization. So when people were no longer drinking milk that was contaminated with the tubercle bacillus, the disease virtually disappeared. And at the same time, another disease, which looks a little bit like it, was recognized, and that's Crohn's disease. It was a very interesting sort of juxtaposition. So in the early days, from ancient times, the idea was to go to a high altitude where there was plenty of sun, it was nice and quiet. People read The Magic Mountain by Thomas Mann, and you stayed in a sanatorium. Apparently life in those sanatoria was not the way it was described in literature. It was a pretty miserable, lonely, waiting to die environment. Public health played a huge role in controlling the epidemics in big urban cities in the United States and everywhere. I remember there were free clinics, there were mobile x-ray units going into the Lower East Side of New York and around and on the Bowery, and there were hospitals. Almost every medical center had a tuberculosis hospital, big ones. The famous Trudeau one in New York. In New York City, there were 3 of them. I'm sure there were in Washington too. And then came the drugs. Waxman discovered streptomycin from a mold, a fungus, and that was the first. And then each one of the drugs has an interesting story we won't take the time to, but it's interesting to read about. And isonicotinic acid hydroside, paraminosalicylic acid, and a bunch of others. And when that happened, I think politics stepped in, and they saved money. They closed the hospitals. Patients wasn't needed anymore, at least for most people. The mobile x-ray units disappeared. And I guess the incidence also declined, but it certainly didn't disappear because tuberculosis never disappears. And they saved a lot of money. Now we live in a world where tuberculosis is striking back. It's striking back in parts of the world that don't have the sort of socioeconomic circumstances we have here. One of the biggest things to accelerate the resurgence of TB was HIV and other immune deficiency kind of states. And then the last batter in the lineup is the fact that people are increasingly becoming resistant to the drugs that exist. So with that as a brief sort of overview, let me briefly introduce our 2 speakers today. So they're going to alternate back and forth in presenting this. So Cliff Barry received his Ph.D. In organic and bioorganic chemistry at Cornell. Following a postdoc at Hopkins, he joined NIAID at Rocky Mountain Lab, and in 1998 was tenured as the chief of the tuberculosis research section of the Laboratory of Clinical Infectious Diseases of NIAID. Now, TRS is like the bridge that we showed, a multidisciplinary group, biologists, chemists, clinical researchers who share a common interest in tuberculosis. These scientists of this group are recognized internationally, and they are the most cited tuberculosis research group in the world. Now, in addition, Cliff and also Chen have worked at the International Tuberculosis Research Center, one in Korea, one in China, and most recently in South Africa. Now, the goal of this operation is to understand sort of the underlying scientific basis of the disease with a view to development of drugs that will be effective globally and have a significant effect on the disease. So our other speaker is Chen, who's a staff clinician in the tuberculosis research section. He went to medical school at the Medical College of Virginia, trained in medicine at Thomas Jefferson, in infectious diseases at the University of Alabama in Birmingham. He has worked for NIH for more than 10 years and was based in Beijing, China for 8 years, where he administered the large NIAID research project in China, primarily in HIV, influenza, and tuberculosis. He's currently a staff clinician in the tuberculosis research section and leads a team that's conducting a number of clinical trials in South Korea, China, and South Africa. His other interest is in the developing of new treatment and diagnostic methods for drug-sensitive and drug-resistant tuberculosis. So we're very grateful to both of you for being here. And I don't know who's speaking first.
Thank you. Thanks, Dr. Arias, for those very kind introductory remarks. So Cliff and I will be talking to you today about The return of the white plague, which Dr. Arias has already described, refers to the sort of anemia that accompanies the disease in certain people. We're going to start with 2 case scenarios just to sort of set the stage for the rest of the talk. So the first case is a 49-year-old male who presents with a cough for 5 months that has gradually gotten worse. The patient's cough is productive of yellow phlegm and has persisted despite over-the-counter cough remedies. His phlegm has occasionally been blood-tinged recently. He does not have a stuffy or runny nose or sore throat. He also reports subjective intermittent fevers because he never actually took his temperature and feeling poorly. He has some sweats at night when he sleeps, but attributes this to not having air conditioning in the homeless shelter where he stays. He has lost some weight, but says this is due to not having consistent meals. He does not feel short of breath and has been able to continue working during the day selling newspapers. He has otherwise been relatively healthy and does not take regular medicines. He smokes 1 pack per day of cigarettes for 10 years, but does not drink or do drugs. No one else around him has been sick that he knows of. On physical exam, this is a thin white male in no distress. His temperature is 99.6 degrees Fahrenheit. His blood pressure is 135 over 72. His heart rate is 96, and his respiratory rate is 20. His physical exam is normal, including the lung exam. On chest x-ray, however, his chest x-ray is not normal. As you can see, especially in the right upper lung field, you see this hazy opacity, and even with this little central lucency here, suggesting a cavity. So now the question is, what are you going to do? He does not look too sick, and chronic coughs are common, especially in smokers. So are you A, do you think this is probably a smoker's cough? Give him some Robitussin and have him follow up in 1 to 2 weeks, if not better. B, this probably started as a common cold that has since developed into a bacterial infection. Give him a Z-Pack to cover the most common bacterial cause and have him follow up in 1 to 2 weeks, if not better. C, this is concerning for active TB. Send a sputum sample to the lab to look for TB, but since he does not appear to be too sick, start empiric TB therapy as an outpatient and have him follow up in 1 week. Or D, this is concerning for active TB. Admit him to the hospital for evaluation and to start empiric TB therapy. Maybe we can have a show of hands. Who thinks A is the right choice? Okay, just 2 of us. Okay, B, what about this? Common cold, we should avoid antibiotics as much as possible. Antibiotic over antibiotic resistance is a major problem. Give him a couple of Z-Pack, and then, he's held off on, this may have started as a viral, we held off long enough. He deserves some antibiotics now. Give him a Z-Pack. Anyone? Any takers? A couple of people? C, whoa, no, this is a little more serious. This is probably, especially with that cavitation on the chest x-ray, this is really serious, but maybe not so serious that he needs to be in the hospital. We should just start him on outpatient TB therapy and see what happens. Any takers? All right, even more of you. And the last one, no, he doesn't look so bad, but this is really serious. He needs to be in the hospital. Admit him and start him on TB therapy and see what happens. All right, I think the C's have it. Unfortunately, you would be committing a grave public health error by doing that because, as you recall, he lives in a homeless shelter. And so he would continue to spread TB to those around him. So yes, first of all, this is active TB, and the big giveaway, or very concerning for active TB, I should say, the big giveaway, of course, is the abscess, the cavity on his chest x-ray. And if he lived in a stable home, where he's away from others, you could possibly start him on outpatient therapy, but since he lives in a homeless shelter, that would not be a good option. So you would have to admit him and do the workup for TB and start him on empiric TB therapy. Okay, so that's the first scenario. The second scenario is the flip side of the TB issue. This is a 25-year-old Asian female who immigrated to the U.S. at the age of 3 with her family. She just started her graduate degree program in microbiology and had a routine PPD placed on her arm due to her area of research. It comes back positive at 22 millimeters, and she is referred to you for evaluation. She had never had a PPD test done before. She reports being otherwise healthy and is on no medications except for birth control pills. She reports receiving a BCG vaccination as an infant and attributes the positive PPD to that. She has a normal physical exam and her chest x-ray is also normal. So what do you recommend? This is, of course, now the first case was a case of active TB. This is a case of possible latent TB, which we'll describe what these are during the talk. So A, her positive PPD is likely due to her previous BCG vaccination. She will always be positive. Nothing further needs to be done. B, she has latent TB infection. Recommend treatment with isoniazid daily for 9 months. C, she has latent TB infection. Recommend treatment with rifampin daily for 4 months. D, she has latent TB infection. Recommend treatment with isoniazid and rifapentine once weekly for 12 weeks. So really the first question is this latent TB infection? Anyone? And what do you do about it? If any takers for A don't need to do anything because there is a definite cross-reactivity between PPD and BCG vaccination. Okay, a couple people. B, all of these are treatment recommendations. Any takers for INH for 9 months? A few people. Rifampin for 4 months? Nobody. One person maybe? And INH rifapentine for once weekly for 12 weeks. Oh, 2 people. Well, I would have to say that D is wrong. So first of all, there is definitely a cross-reactivity between BCG and PPD, but the recommendation from the CDC is that to disregard that as when you're evaluating for latent TB infection, because those who receive BCG as an infant, the people from those countries, TB is generally endemic in those countries, and so you cannot differentiate between a reaction due to cross-reactivity with BCG versus a true infection and latent TB. And so in the US, the CDC guidelines is to disregard a prior history of BCG vaccination. So the answer is to treat. And the problem with C and all 3, B, C, and D, are all recommended treatment regimens. And the reason that C and D are incorrect is that they both involve a rifampin, which has drug interactions with birth control pills, which she is on. So unless you want her to have a decreased effectiveness of her birth control pill, which may make her not too happy, then you should give her B. Okay, so what is TB? TB is a small aerobic bacillus with a high lipid content in the cell wall, and the cell wall therefore then retains certain stains even after an acidic wash, and that is why it's called an acid-fast bacilli. There's 2 types of stains that are commonly used. One is called the Zeal-Nielsen stain, which is what you see on the lower right, which is that sort of pink, that red rod is the bacteria. And the other is an auramine-rhodamine stain, but you have to use a fluorescent microscope so that the bacteria will light up, which you see on your lower right. TB has had a long history, as Dr. Aris has already mentioned, reports of it even in mummies. And it's been known as consumption because it is, or wasting disease because people get really, really thin, and also the white plague. It was believed to be hereditary. That's understandable since it's transmitted oftentimes in the household. So until 1865, when Jean-Antoine Villemin demonstrated that TB was infectious by transmitting it from humans to rabbits, cattle to rabbits, and rabbits to rabbits. Further, in 1882, Robert Koch identified the actual bacterium, Mycobacterium tuberculosis, and he subsequently won the Nobel Prize for his work in TB. Before the 1940s, there was no treatment for TB, and people often just resigned themselves to die. There were these sanatoria where people received so-called treatment with bed rest, good nutrition, fresh air, and sunshine. And Edward Livingstone Trudeau opened the first sanitarium in the US, and in his story is kind of interesting. When he was 19, he watched his older brother die of TB. 1 year after medical school, he contracted TB, and he just decided that he would go and enjoy the rest of his days and wait to die, so he went to his favorite resort in the Adirondacks, but instead he slowly got better. And he really believed that his improvement was due to a healthy diet and outdoor exercise, and he felt that his belief was confirmed by some experiments he conducted in rabbits, and therefore he established the Adirondack Cottage Sanitarium in 1885, which you see here. It started as one little cottage and subsequently expanded to encompass the whole campus. Again, back in those days, there was no real good treatment, but there was a lot of public health campaigns. You can see that there was these different advertisements to recommend people not to spit, because tuberculosis could be spread that way. And some of you may even remember the Red Cross Christmas Seal campaigns to really try to raise funds to support tuberculosis.
Right, so that's the that's the contemporary history of tuberculosis. The real story turns out to be even more interesting and has been illuminated in recent years as we've learned more and more from the genome sequences of tuberculosis. Now, the sort of urban legend, if you will, of tuberculosis is that humans first were infected with tuberculosis when we domesticated cattle about 6,000 to 8,000 years ago, and that it started as a bovine bacillus and transmitted itself to people through the close interaction between people and humans. That turns out to be completely wrong. As we later learned when we sequenced the genome of the primary bacillus that infects humans and the primary bacillus that infects cattle, it became very clear that there had been loss of genetic information in the strains that infect cattle, and that the only possible mechanism for transmission was that we gave it to the cows when we domesticated them, not vice versa. Nonetheless, that was the contemporary story about 10 years ago. But again, through extensive genome sequencing efforts of different mycobacteria that infect, and mycobacteria infect virtually all mammals, right? So there are mycobacteria strains that have very specific host tropisms, so that they only infect mice, or they only infect cows, or they only infect rabbits. I mean, every species has its own flavor of Mycobacterium tuberculosis. But it became quite clear that there were major lineages, even within contemporary humans, that were geographically restricted. And that geographical restriction turns out to be fairly tight if you look amongst people from a given region. So people from Southeast Asia will have one strain, people from Central Asia will have a different strain, European, American lineages. So this breaks out by geography. And by sequencing those, gave rise to this sort of lineage map that you see here, where the progenitor bacilli were all present in Africa and moved with us as we migrated out of Africa to various geographies around the world. And that's the out of Africa hypothesis for the tuberculosis field. And some of the evidence for that relies on looking at these genome sequences and tying them back to what's the most probable ancestor of those. And then comparing, and this is, people have debated how true this is. This is the origin of all the different lineages. So this is the Southeast Asian lineage, these are African lineages, this is Eurasia, et cetera, of TB. And these are the mitochondrial DNA sequences of humans, arranged roughly in the same order and with the same color scheme. So their African humans are here, Southeast Asian humans are here. And you can see there's a sort of an amazing coincidence of evolution between those two trees, so that it became obvious that TB was evolving with extant human populations and really specializing in the kinds of humans that carried it with them to their ultimate destination. So that was a good story. But we learned last year that even that wasn't really true. And we learned that through this amazing study that was a collaboration between a team of archaeologists and a team of mycobacteriologists who were looking at this map that's too small to really see is Peru. And this is a river delta in Peru and several archaeological dig sites. And these two spines were excavated from those remains at those two sites, or those three sites actually. And they represent, through careful dating experiments, those represent remains from about 1,000 years ago. And we know they had tuberculosis. And why do we know they had tuberculosis? See this characteristic curvature of the spine. So this has already been referred to today. That's Pott's disease. So that's TB of the spine, and it results in this very characteristic humping or deformation of the spine. Now, again, because we can very carefully dissect those samples, these investigators were able to sequence the genomes of those mycobacteria from those spine samples and assemble intact genome sequences from TB as it existed 1,000 years ago. And when they did that, what they noted was all the contemporary human strains fall up here. These are all animal strains down here, and these are the ancient Peruvian humans. And what they noted was these are most closely related to progenitor strains of M. pinnipedi. And pinnipedi is another one of those very specialized mycobacterial species that only infect seals. So strange but true, it appears that about 1,000 years ago, TB, and now this upsets a lot of apple carts, but this appears from the genetics to be what really happened, that TB transmitted from seals into humans and possibly emerged in South Africa and Africa at about the same period in time. The important thing there is the date, 1,000 years ago. That's pre-European contact with South America. So that means that the other myth, the other urban legend that accompanies TB, that it really transmitted to the New World when Europeans first came in contact with South Americans, is also wrong, because it emerged almost contemporaneously in both South America and in Africa. And that's a finding that people are still trying to get their heads around. How did it transmit from seals? Were we eating seals? Were seals coughing on people? Was there some close contact between seals and people, something unnatural happening? We don't know, but in any case, it really does appear that this disease probably did emerge from the seal bacillus to become the human bacillus that then later spread contemporaneously from both South America and from Africa. Okay, Ray.
TB drugs were first identified in the 1940s. In 1943, streptomycin was discovered, and subsequent to that, isoniazid and PAS also became available. And as a consequence, by the 1970s, Sanitera really became obsolete, and a lot of them were closed because the treatments were actually quite effective. There was actually quite a lot of confidence in TB treatment at the time, and a lot of complacency as a result developed. And consequently, there was a resurgence in TB in the 1980s, not just due to complacency, but reduced funding, increased immigration, and the HIV epidemic as well. And around that time, the development of multi-drug resistant TB also became an issue, and was as evidenced by this publication in the New England Journal with first author Tom Frieden, who is currently the head of the CDC. So since then, these are some slides from the CDC. You can see that, rates of TB, these are rates in the US, TB went down, and then there was a rise again in the early 90s. And since then, there's been a slow and steady decline in the rates of TB until 2013, there were about 9,500 cases total reported in the US. And from this overall incidence rate, these are cases per 100,000 population in the US, and you can see that over the last several years, the rate has continually declined until in 2013, the most recent year we have data, the rate is 3 cases per 100,000. Now, to give you some context as to what this means relative to the rest of the world, Canada's rate is 5 per 100,000, the UK is 13, China is 70, Russia 89, South Korea 97, India 171, South Africa 860. Swaziland, the small country right next to South Africa, has the highest rates of TB incidence in the world, 1,380 cases per 100,000, over 400 times our rate. It doesn't help. Probably part of the reason Swaziland has such high rates is because they have the highest rates of HIV in the world as well. About 26% of the adults are co-infected with HIV, are infected with HIV. Here in the U.S., the average is 3, and you can see that we're right next to D.C., which has a rate about 5.5. So D.C. is above average in rates of TB in the U.S. And in the U.S., in TB is most commonly or primarily now among those who are foreign-born. You can see that around 2001 is where the rates in the, among U.S.-born came down below the rates of the foreign-born. So the rates in U.S.-born have been steadily dropping, whereas the rates in foreign-born have been relatively steady. But as we look at it, in fact, the rates among the foreign-born have been declining as well. And so it's still higher in the foreign-born, but rates among foreign-born and U.S.-born have all been declining over these last several years. An estimated 1/3 of the global population is infected with TB. Most of this is probably latent TB. And in 2013, the year we have, the latest year for which we have data, there is an estimated 9 million new cases of TB in the world, 13% of which were co-infected with HIV. 1.5 million deaths due to TB. There are extreme global disparities in the disease burden. India has 24% of the world's total TB, China 11%, and Africa as a continent has 25%, along with the highest rates of infections and deaths per capita, and 80% of the HIV-TB co-infected cases. So although the overall global TB incidence and mortality rates are declining, MDR rates, however, are still increasing, multi-drug resistant. So these are just some figures from the WHO Global TB Report from 2014, and you can see that the global incidence and prevalence are both declining, as well as mortality. This is the Stop TB Partnership goal of a 50% reduction in prevalence and mortality from the 1990 rate by 2015. So the goal is to reach this half of the 1990 rate by 2015. You can see we're quite closely approaching those numbers. But there is also another goal of eliminating TB globally by 2050, and I think we're not very close to that at all.
Right, so these are some modeling studies for what it would take to achieve the Millennium Development Goals agreed to by the G8 countries for elimination of TB by 2050. This was done by Chris Dye, who's a good friend of mine at the World Health Organization, the lead epidemiologist in charge of all infectious diseases now. And the blue lines in each of those graphs, so the top on the left is cases and the bottom is deaths, and the blue line represents our current achievement in terms of reducing the number of cases and the number of deaths. Currently, we've got about a 2% reduction per year in the number of cases and a 5% reduction in the number of deaths. And the reason for that, the contrast between this and the previous slide numbers, is the total burden of disease is quite difficult when 50% of the patients are never diagnosed correctly. So it comes back to this: can you actually pick out a TB patient in a population when you're presented with cases like Ray was presenting? Chris estimates that if we employed all the resources that we had at our disposal internationally for public health control programs, we could achieve a 10% reduction rate per year, which still would fall well short of the goal of eradicating the disease by 2050. And we could knock the number of deaths down quite a bit. But we would need to achieve, beyond our current technology capacity, we would need to achieve a 20% reduction per year in the number of cases and 14% in the number of deaths to actually eradicate the disease and do as the G8 group agreed to try to achieve by 2050. And on the right-hand side shows the kind of reasoning for some of this. I think it's important to understand that when we treat active TB, we do eliminate mortality quite quickly, but we actually don't have that big an impact on the number of cases. And the reason for that is because by the time somebody figures out they're sick with TB, gets an appropriate diagnosis, and gets into the healthcare system to be treated for that disease, they've already transmitted the disease to 10 more cases. They've already transmitted, on average, about 10 to 10 people at that point. So just treating the active disease will only very slowly get us towards the numbers that we're looking for. So you can eliminate a lot of deaths that way, but you don't actually reduce the cases because they've already transmitted before they get into the healthcare system, get diagnosed, and get treated appropriately. Really, the most effective thing you could do would be to treat both active and latent TB. So this is the treating latent TB as this light blue line. Preventing infection, which is of course the goal of a lot of vaccine efforts these days, doesn't really have a big impact on the number of cases in the absence of treating the active cases. And you can argue about why that is, but really the best scenario is one in which we can identify, treat, and eliminate both active and latently infected individuals globally. And that's a very ambitious and difficult goal, and I'm going to tell you a little bit later how people are approaching that. Now, all of those numbers and all that incidence and mortality is based on one big, very arguable assumption. And that assumption is that the bacteria stays the same, that things don't change in time. We have lived with tuberculosis since, as a global population, since we were primarily hunter-gatherers and very loosely distributed, very thin populations, very low density people, not a lot of contact. And strains of TB evolved to be able to deal with that, and they evolved in a certain way so that they favored reactivation in latent cases at certain periods in time and certain points in people's lives. And the world has changed. So this is downtown Seoul, one of the places we work, and you can see the differences. This is a hugely diverse, compact population density, is about the highest on the planet. And in that environment, the same sort of evolutionary strategies that favor continuation of the bacteria change dramatically over time. And we've seen that happening in real time. And this is a study that just came out in Nature Genetics that we contributed to with a bunch of sequencing efforts from our patient cohorts in South Korea. And this shows radiation of what we've called, what the global community has called, and China hasn't objected yet, the Beijing lineage of strains. Now, the Beijing lineage has been associated with everything that's bad about tuberculosis. More epidemic spread, more mortality, more drug resistance, everything bad about tuberculosis. And it used to be primarily found in Beijing, but it's now been reported from virtually everywhere. It's the most prevalent lineage in many communities in South Africa, for instance. It's been found in South America, it's been found in North America, it's been found throughout Europe. So this lineage is spreading. And it's spreading in real evolutionary modern time. So this is not just a small concern to us. This is a big concern because this lineage actually is, in many people's estimation, hyper-virulent in some way, and that's the basis for its spread. We can tell they're all Beijing lineage and they're all related to each other, and you can even sort of quantitate that. And this is the mean allelic difference from the progenitor Beijing strain plotted against the distance from the Yangtze River basin where the Beijing lineage is supposedly emerged. So you can watch that evolution happen. You can watch the strain radiating out from China. And people have argued about the reasons for that evolution, but the one I find biologically most plausible is that this strain has emerged because we've adopted widespread BCG vaccination programs. That BCG vaccination coverage is fairly uniform throughout most of the world, with the exception of the US and certain parts of the developed world in Western Europe. And that vaccination imposes selective pressure on the bacteria, and this strain is particularly good at not being subject to killing by many of the immune mechanisms that we employ in that particular vaccine strategy. So this is natural. This is really natural selection at its finest, right? The organism has seen the selective pressure we chose, the weapon we chose to throw at it, and it's evolved a strategy around that selective pressure, and it's re-spreading through the human population. So don't be fooled by our apparent success, which a lot of people are, and think that this is a disease that's on its way out. It's a disease that's reinventing itself. It's a very, very changeable and adaptable organism that has lived with humankind for its entire history, and we're not really close to eradicating it yet.
So Cliff mentioned that another hallmark of the Beijing strain is that it is noted to be more resistant to drugs than other strains. Multi-drug resistant TB is defined as TB that is resistant to two of the main first-line drugs, isoniazid and rifampin. And consequently, cases are much harder to treat and require a much longer treatment duration. Overall treatment success rate among just regular drug-sensitive TB is about 86% globally, whereas in MDR TB, it's down to 48%. And it's because it requires, we only have less effective drugs that are more toxic and requires about 2 years of treatment for MDR TB in comparison to 6 months for drug-sensitive TB. So you can imagine that people, the completion rates for MDR TB are much lower than for drug-sensitive TB, and therefore the success rates are also much lower. In 2013, there were estimated 480,000 new MDR TB cases in the world, with 210,000 deaths. And the rates of MDR TB are increasing. About an estimated 3.5% of new cases in 2013 were due to MDR TB. That means primary transmission of the drug-resistant strain. It wasn't that the person didn't take their drugs well and became resistant, but that they were infected with a drug-resistant strain. 20.5% were previously treated cases, so they may not have taken their drugs too well the first time around. India, China, and Russia together contribute more than 50% of the global MDR TB burden in the world. And an estimated 9% of MDR TB cases are actually what is now known as XDR, or extensively drug-resistant. And extensively drug-resistant TB is MDR TB, that is TB resistant to isoniazid and rifampin, that is, in addition, also resistant to the second-line drugs of the fluoroquinolones and the second-line injectable agents. So 4 classes of drugs are now resistant for XDR TB. There's a very high rate of mortality associated with the late-stage HIV infection. XDR TB made a big splash in the world with this publication in The Lancet in 2006, which described a cohort of patients in South Africa around a town called Tugela Ferry. And in this analysis, they sampled 1,539 patients. And among them, they found TB patients. Among them, they found 14.4% were MDR, and 3.4%, or 53 patients, were actually XDR TB patients. They took a closer look at these 53 XDR TB patients, and they found that among the 47 on which they had data, half of them, 55%, had no previous TB treatment. So they were, more than half were primarily infected with an XDR TB strain. Among the 44 on which they tested for HIV, all 44, 100%, were HIV positive, with a median CD4 count of 63, which is very low in the range of AIDS. 52 of the 53, 98% XDR TB patients died, and among 42 with confirmed dates of death, the median survival was only 16 days. You can see that the 50% was only at 16 days. So very late diagnosis and rapid progression to death. And 70% died within 30 days of the sputum culture collection. So you can see XDR-TB is very, very severe disease. And as a result, in this 2013 publication, which CDC named their top 5 global infectious disease threats from the year 2012, number 1 was avian flu. Number 2, cholera. You'll recall that there was a big epidemic after the Haiti earthquake in 2010. Number 3 is wild poliovirus. Number 4 is enterovirus 71, which causes hand-foot-mouth disease. And of course, this past year we had enterovirus 68 make an epidemic in the US. And number 5 was extensively drug-resistant tuberculosis, so a major global health hazard. TB causes a granulomatous inflammatory process with macrophages, lymphocytes, and fibroblasts recruited to the site of infection. Then the bacteria, the human immune system either will eradicate the infection completely, or if not, will try to wall it off by forming a granuloma to sort of contain it and suppress it. And that is what we call latent TB, where the TB is in the body, but it's walled off in probably a granuloma and not causing any sort of problems for the patient. Granulomas, over time, if it progresses, may classically develop a caseous necrosis in the center, perhaps an active disease. So studies show that among those who are latently infected, an estimated 10% will develop active disease over the course of their lifetime. Of this 10%, half or 5% will develop disease in the first 2 years after infection. So if you know when you were infected, the first 2 years after that are considered higher risk. And then the remaining 5% is over the rest of your lifetime. So 10% total with half of that risk in the first 2 years. If the person is co-infected with HIV and is untreated, that's a risk of 10% of activation per year. So you can see HIV increases the risk of active disease markedly. Infection can be spread via the bloodstream, which is called miliary TB, and this is more common in young children and in those who are immunocompromised. And infection naturally waxes and wanes. Individual granulomas or individual TB lesions can get better or get worse on their own. In general, without treatment, they will tend to get worse. But in some cases, for example, in the sanatoria days, some people were able to get better on their own too.
So that's the sort of old school picture, this dichotomous view of TB, of latent tuberculosis and active tuberculosis. And some of you may remember the sort of old cartoon versions of the TB bacillus called Huber the tuber, who went to sleep in your lungs and built a little cocoon. That's the granuloma in which he went to sleep like Rip Van Winkle and then woke up when you got old or sick for some reason. We've come to appreciate in the last 10 years, primarily through studies in close relatives of ours, various species of non-human primates, that this dichotomous picture of disease is really not at all what happens in people. It's what happens sort of from a medical perspective, but actually the infection is much more of a spectrum of disease than it is a single dichotomous latent or active designation. And I'm just summarizing that in this slide, and I like this sort of hand-drawn version of this, because this is what happens when you take this species. This is cynomolgus macaques, and these are studies that were primarily done at the University of Pittsburgh by Joanne Flynn. And you infect them with tuberculosis, and what you see is just what you see in humans. Some of them will go on to develop active disease immediately, develop a fulminant disease, but most of them develop a clinically latent disease, just the way you define it in people. So they convert their skin tests, they have big whopping Mantoux reactions, but they don't have any symptoms. They're not sick clinically. Now, the nice thing about the cynomolgus macaques was we could take them apart afterwards and ask what was going on in their lungs. And so this is what we saw. And this is a picture of the lungs and the liver and the spleen. And you can see each black dot represents lesions that are spread that actually where bacteria were cultured, and there was pathology consistent with tuberculosis. And you can see just visually that the active disease monkeys have a wide variety of different amounts of disease. And the latent monkeys all have much less disease and much fewer numbers of lesions. But then an equal number of those that we would consider latent clinically had this sort of subclinical disease, where they had what looked like active processes happening in their lungs, lots of bacteria, but they weren't sick, and they weren't coughing up bacteria, and they weren't losing weight. So again, these are just like clinically infected humans. Now, when we bronch these monkeys and plate them out and look for CFUs, they have bacteria in their airways. And so it raises the disturbing specter that there are quite a few people walking around with subclinical disease that we would consider latent. No symptoms, they're not sick, there's no reason they would go to the doctor to have that diagnosis, that are active reservoirs of transmission of tuberculosis. And we've sort of we've tried to eliminate the notion of latent disease from our vocabulary, and instead talk about it today as a spectrum of disease that ranges from clinical disease to complete elimination of disease in some people. And emerging evidence from clinical studies we're doing in South Africa at the moment suggests the same spectrum happens in people. And so that takes, the nice thing about that is that takes an intractable problem, right? A third of the world's population is walking around with latent disease, and breaks it down into a diagnostic problem. Can we identify those people in this region who are more likely to progress to active disease? And can we intervene in a much smaller number than a third of the planet's population and actually have a much bigger impact on the way we're trying to control the epidemic, instead of just focusing on people at the very extreme case of having developed active clinical disease?
So, Cliff just presented that TB is actually a spectrum of illness. But unfortunately, despite our modern technology and diagnostic methods and all the advances that we have, we still are not able to diagnose those different stages of infection, and we are left with just latent or active. And in fact, sometimes we can't even tell the difference between those. So for example, the PPD, which is just measures the immune response to some TB antigens that are injected intradermally, that tells you that you've been exposed to TB. It doesn't tell you whether that TB is active or latent. So, but this is one of the long-standing tests that we've been using, the PPD, and you inject 5 tuberculin units into the skin, and the cutoff again is interpreted based on your risk factors. So, the smallest cutoff of 5 millimeters is if you're severely immunosuppressed, such as if you're HIV infected or you're on immunosuppression, like you have a transplant, or if you have considered a high-risk person, such as a recent contact of a TB case. Then you would have a 5 millimeter cutoff. If your PPD in between 48 and 72 hours is above 5 millimeters, then you're considered positive. On the other hand, if you're completely normal, with no risk factors of anything, you have a 15 millimeter cutoff. And you can imagine that it's very difficult to measure that very accurately. So if you're 14 versus 15, I mean, who can measure that really, really accurately? And everyone else is in between, which is considered above 10 millimeters. If you're an immigrant from an endemic country within the last 5 years, if you're a drug user, if you're a healthcare worker or a laboratory worker, or if you have certain illnesses such as diabetes or other risk factors that put you at risk for active disease, then you have a 10 millimeter cutoff. So you can see that really these are somewhat artificial, and it's really a spectrum. More recently, we've developed another test, which is a blood test to identify previous exposure to TB. And this is a little more specific than the PPD. As we mentioned earlier in the beginning, PPD does cross-react with the BCG vaccination, but the interferon gamma release assay does not. And this is basically a measurement of interferon gamma release by T cells that have previously been exposed to TB. And so here we have their TB antigen. You have a T cell, antigen T cell that has previously seen TB before. And then you have an antigen presenting cell. So the antigen presenting cell will then take up the antigen and present that to the T cell, the TB sensitized T cell. And as a result, this TB sensitized T cell will produce interferon gamma. And this interferon gamma can then be measured. And if you have a measurable response, then that is considered positive. The assay is not affected by BCG, but there are 3 other species that will cross-react because of the antigens that are measured, ESAT6 and CFB10. Again, this test does not distinguish active from latent disease. There are currently 2 interferon gamma release assays that are used that are commercially available. One is called T-spot TB, and this uses a ELISpot assay to measure the interferon gamma, and then you actually count the number of spots, each spot supposedly representing a interferon-producing T cell. And if you have more than 8 spots, that's considered a positive test. The other assay that's used is a quantiferon TB Gold, and that uses an ELISA methodology, and so you can measure then the interferon gamma concentration that is produced, and a concentration of more than 0.35 is considered a positive result. So if you are diagnosed with latent TB, that is, if you're positive on one of these tests, and then you are evaluated for active TB, typically with a chest X-ray, and you are not found to have any evidence of active TB, then you are considered to have latent TB. As you'll recall, an estimated 10% of those with latent TB will develop active TB. So here in the US, and this is not much done in other parts of the world, but in the US, we treat latent TB to try to kill off the latent infection to prevent it from becoming active TB. It probably works at about 90 or 95% efficacy. And we have several different regimens that are recommended. One is isoniazid once daily for 9 months. A previous recommendation for rifampin and PZA for 2 months is no longer recommended because it caused high rates of hepatotoxicity. And finally, rifampin daily for 4 months. And these are recommendations from the CDC publication, Morbidity and Mortality Weekly Report, MWR, from 2000. So these have not changed in the last almost 15 years. There is, since then, one new regimen that has been recommended, which is INH plus rifapentine by directly observed therapy once weekly for 12 weeks. And this was found to also be very effective. So it may be more convenient for some people, but this one, in contrast to the other regimens, is recommended to be done by directly observed therapy. Now, treatment of TB, if the evaluation of TB finds that the patient actually has active TB, the treatment of TB also hasn't changed in the last 15 years or so. There's an intensive phase which involves 4 drugs: isoniazid, rifampin, pyrazinamide, and ethambutol, plus pyridoxine, which is vitamin B6 to try to prevent some toxicity from isoniazid. And this is given for the initial 8 weeks of therapy. And the ethambutol can be discontinued during that time if sensitivity testing shows that the TB is sensitive to all of the drugs. After the 2-month intensive phase comes the 4-month continuation phase, where you drop 2 drugs and you continue only isoniazid and rifampin. And these drugs are then continued for the remaining 4 months. Occasionally it's extended to 7 months for 9 months total if you have a cavitary disease at baseline or are still sputum culture positive at 2 months. But typically, treatment for drug-sensitive TB lasts about 6 months. There are some common side effects to these drugs. The first 3 typically can cause hepatotoxicity. Isoniazid also has some peripheral neuropathy, and that's why we give the vitamin B6 in conjunction with it. Rifampin classically causes the orange-red discoloration of all body fluids, urine, saliva, tears. It can stain contact lenses and such. Occasionally it can be associated with some thrombocytopenia. Rifampin also is most notoriously has many drug-drug interactions. So you have to use this drug with caution with people with already taking other drugs. Pyrazinamide can cause elevated uric acid and therefore gout. And finally, ethambutol is associated with color, discrimination change, or visual acuity change. So those need to be monitored for patients on ethambutol. More recently, about 5 years ago in 2010, there was a new diagnostic method that was developed called the Expert MTB-RIF. And this was quite revolutionary because this test not only identifies infection, that is MTB, but it also identifies drug resistance to one of the first-line drugs, rifampin. Now, previous to this technology, to get drug resistance testing, you have to first collect sputum from a patient and send it to the lab, where they will culture it or put it in the incubator and let it grow. And that growing process, depending on how much sputum, how much TB is in the sputum, can take anywhere from 1 week to 6 weeks. Once this TB grows out and you discover, oh, this person actually has TB, then you have to take some of that culture and grow it again in the presence of drug to see whether it's sensitive or resistant to that drug. So you can see that this whole process will take several weeks to possibly even a few months to get results of drug resistance testing. So this little machine called Expert MTB-RIF was quite revolutionary because you can get a diagnosis of TB and a diagnosis of rifampin sensitivity or resistance in 1 hour and 45 minutes. And all you need to do is collect some sputum from a patient, mix it with some what's called sample reagent, and let it sit for about 15 minutes in the cartridge, and then put it in the machine. The machine will then run a polymerase chain reaction to look for specific genomic sequences for TB, as well as for rifampin resistance. And rifampin resistance is felt to be a surrogate marker for MDR-TB. An estimated 90% of people who are rifampin resistant are also isoniazid resistant. So this was quite a revolutionary advance in diagnosis, in increasing the speed at which you can diagnose TB and MDR resistance. This machine is, as you can imagine, quite expensive, but it's been supported by donations, especially from the Gates Foundation, and so now it's being ramped up in most countries across the world. And cartridges also, you have to purchase cartridges, and the machine, I think the negotiated prices is still about $20,000, and cartridges are about $20 is the negotiated price. But still, many countries are now using this, and 7.5 million cartridges have been procured by 108 of the 145 eligible countries for the concessional pricing. The treatment for MDR-TB is much more complicated. Drug-sensitive TB was for 4 drugs for 2 months and 2 drugs for 4 months. And now for MDR-TB, you have to have up to 5 or more drugs for 2 years, up to 2 years. And you just basically use the drugs, any drugs that you still can use. So Group 1 are the first-line drugs that might still be available. So if any of these are still sensitive, you would use them. Then you would pick one drug from each of the remaining categories. These are the second-line injectable agents. And so you would use these for, first 8 months or so. It's an injectable, so it's usually given intramuscular, and it's not very comfortable. And then you would pick a fluoroquinolone to add. And then one of these bacteriostatic agents, ethionamide or prothionamide. And finally, you would pick something from Group 5, which is known as agents with an unclear role in MDR-TB. So basically, drugs that may work, and you just try because you have nothing else to try. And these have a number of different drugs. The linezolid, actually, there's been a lot of more data recently showing that linezolid actually works quite well. But you can see that this is just a large number of drugs with a large number of side effects for a long time. And it's a very difficult disease to treat.
Right, so obviously part of the answer is we need new drugs, and where are the new drugs going to come from? And this sort of notional TB drug pipeline shows you what things are currently in development. I say notional because this is changing on a constant basis, and we all sort of felt reasonably good about this pipeline a few years ago because we had quite a few things that were in phase 3 trials that were potentially new agents and no pre-existing resistance, and we had quite a few things that were in phase 2 studies, and we thought we were making good progress towards building a more robust drug pipeline for the treatment of tuberculosis. That all changed last October when we, using our old clinical trials methodology, which is based on measuring how fast bacteria clear from sputum, we evaluated that for 3 different phase 3 regimens that involved treatments that were predicted to shorten the duration of treatment to 4 months, right? We're trying to incrementally work this down to something where you can actually manage to keep patients on for the full duration of chemotherapy and get them a stable cure. And these 3 trials in the New England Journal in October, late last year, really torpedoed our ship of hope towards the TB drug pipeline, because all three of them were clear and spectacular failures. All of the phase 2 data had not translated into phase 3 endpoints that we could actually measure. And we really didn't know where we were going from there or how optimistic to be about our drug pipeline. In fact, that sort of catalyzed a couple of things. I think one was the writing was on the wall, that we really didn't know how to do good clinical trials for this. And one of them, which Bill Gates played an incredibly important role in, was this effort that was called the CEO Roundtable that continues to today. And what Bill did was contact the heads of many major pharmaceutical companies. They're listed up there if you're interested, and said, look, guys, you need to do something about TB before this epidemic gets completely out of control. And he had the clout, the political clout, to get them to sit down around a table and talk about what the drug companies could actually do to help develop new drugs for treating tuberculosis and other tropical diseases, but with a particular focus on tuberculosis. And as a result of the CEO Roundtable that continues every year, the Gates Foundation, the pharmaceutical companies, NIH, and a couple of academic institutions formed what's called the TB Drug Accelerator, which is this partnership effort to try to leverage what the pharmaceutical industry does very well with what the public health needs and resources that exist within the public sector, broadly speaking, meaning the academics and the government collaborators. And the idea with this was that the companies would initiate this collaboration by supplying compound libraries that would be screened in a series of different in vitro assays in a normal way. And they would do that without telling us all the structures, right? They're not going to give us the family jewels of what the drug companies do, but they'll give it to us blind. We'll screen those compounds, or the academic groups within it would screen it. And then we would reach out across the companies and look for a way to build this quickly into compounds that had interesting properties that we wanted to try to get into the clinic. And those would feed into a hit and lead optimization programs with the stated goals of, by 2018, having this number changes, but having 5 to 8 new preclinical candidates, and by 2024 to have a 1-month 3-drug regimen achieve proof of concept in clinical trials. Those aren't goals that I think are particularly realistic, but they are goals that were set for us by the CEOs of those pharma companies and Bill Gates sitting around a table saying, wouldn't this be great if we could do this? So we're right at the center of this activity. We do a lot of the screening. Some of these people are even in the audience now. We receive compound plates from these companies in the biosafety level 3 facility in building 33. We run screens on those companies' compounds. And you can just look at the numbers here. And this is an old slide, so it's certainly out of date now. But we're into the millions and millions of compounds that have been screened against tuberculosis, all of which come from theoretically drug-like sources within the pharma company libraries. And the reason this works, and I'm just showing you an irrelevant structure here, but we'll just say this was a structure we got as an HTS hit. Normally, what we would do with that and any related compounds is start doing chemistry around this to try to build SAR. But the way the drug accelerator works, what we do is we disclose the structure of this hit to all the companies that are involved, and we ask them to search their analogs, search their libraries for analogs of that. So in one case, for instance, we'll get 600 related structures from 7 different companies, and we'll send the compound, the hits and related compounds to all the companies for their standard preclinical screening assays that are all meant to reflect toxicology and drug likeness. And we'll have this package of information that takes less than half a year to get together by having these companies work together and work with us. And previously would have taken a team of chemists and biologists, 5 people years, 5 FTEs working for 5 years to generate that same quality of information around a hit package. Currently, we estimate there are about 3,200 different compounds in development across 150 different discrete series. So we're making good progress towards that, and we need to keep that moving. The other thing that we've realized is that our preclinical animal models are really not good. And this is a direct quote from one of those 3 papers I showed you in the New England Journal of Medicine, which explains that basically we used to trust the mouse data for predicting how we were going to use drugs in people, and really the mouse is not giving us good information, and there's lots of reasons for that we can talk about. And in response to that, what we've done also here at NIAID is develop an animal model for disease that really reflects much more what we see in humans. And this is a small New World primate species. This is the common marmoset. And this animal is nice for a variety of reasons, mostly because it's small, and so you can afford to test a number of compounds in it with relatively little compound material. But it also develops all the same characteristics that you see in human disease, and so it should be much more predictive of what we would observe in the clinic. The other nice thing about marmosets is that 80% of live births are twins. And so you have born in your experiments, you have the perfect control in every litter of animals. So you can do one animal on a drug, and one animal on a related drug, or one animal untreated, and get a really good estimate of what the specific activity is. We've also developed, with support from both Intramural and the Gates Foundation, a small animal PET-CT imaging technique for doing live imaging. This is a PET detector and this is a CT detector. And we use that for getting more than just CFU endpoints on these animals. And I won't go into a lot of detail on that. In fact, I think I'll skip that. But what you get are quantifiable images that allow you to make comparisons between drugs or drug regimens. And so this shows two regimens. One is the standard that Ray's already referred to, that you treat every drug-sensitive TB patient with. This is an animal pre-infection. This is an animal 6 weeks after, this is 4 weeks after infection. This is 6 weeks after infection. This is after 2 weeks of treatment with that 4-drug combination, 4 weeks and 6 weeks. And you can see, and these are inherently quantitative techniques. So you're measuring radioactivity emitted from this positron-emitting isotope of glucose. And so you can immediately capture that information and measure a magnitude of change from that. This is a regimen that was used in people in the early 70s. It's streptomycin and isoniazid. It's not a very good regimen, and you see the corresponding not very good response in the PET-CT characteristics. Now, the other nice thing about that, of course, is we can translate that all into people. I'm not going to go into the quantitation of this, but this is the kind of quantitation we can do in the animals, and we can do the same thing in people. And just a month or two ago, we published 2 of these studies. The first prospective longitudinal study of patients treated with MDR disease with standard drugs and following their disease by PET-CT resolution, and in non-human primates, showing that the results we saw in the monkeys were very similar to what we saw in people. And this is some amazing technology, and there's some amazing advances in image processing that allow us to really look in detail at what's happening within the lungs of infected people. So this is a patient who, at study entry, has mostly middle and lower lobe disease. This is just getting rid of this lung and turning the image so you're looking as though you were standing in the heart. You can see the middle lobe partially collapsed, and the lower lobe is completely filled with this consolidative disease. And then 2 months later, we get the same patient in, we PET-CT scan them again, and you can see how much the disease is resolved in that 2-month period of time. And more than that, you can quantitate it precisely down to how many milliliters of disease, what did the disease look like, how fast was it responding to those particular drugs. We showed by following those patients up for a very long time, there were 2 years on treatment and then a year of follow-up after that, that these changes in these PET-CT markers were predictive of how those patients did in the trial. So whether they were actually cured or not, we could establish at 2 months who was going to go on to develop a durable cure of disease. And so we think we've bridged the gap between the animal studies and the human studies with a technology that will hopefully help us better pick those agents that can actually shorten disease. Okay, we've got 10 minutes left, so we're going to do vaccines real quick.
Yeah, so we're going to just finish up with a brief word about vaccines. As many of you know, we've also already mentioned about the BCG vaccine. It's a vaccine developed in 1921 based on the Mycobacterium bovis, and it does have some protective effect, but it's not actually very good for pulmonary TB. It does protect against disseminated TB, TB meningitis, miliary TB, particularly in children, but it doesn't seem to prevent actual infection or pulmonary infection. And it doesn't seem to do anything for adults. And it does cross-react with the PPD, so it does make interpretation of the PPD somewhat problematic. There are many vaccines in development right now, and with two different strategies, either to boost the existing BCG vaccine because so many people have already gotten it, or to replace the BCG vaccine completely. These are the sort of vaccines in trials at the moment, and almost all of these follow the same strategy, which is to try to sensitize the immune system to the TB antigen such that when the body sees the TB antigen again in a sort of a real-life infection, then it can fight it off. But unfortunately, this doesn't always work because this vaccine right here has actually completed a clinical trial published in the Lancet in 2013. This is a trial designed to boost BCG efficacy. So given to babies who already received the BCG, it was a double-blind, placebo-controlled trial, and almost 2,800 infants were enrolled in Cape Town, South Africa. And you can see that after 1 week, there was a strong measurable immune response in these patients, in these infants. And so people were very excited. They thought this trial was well on the way to success. But ultimately, at the end of the day, the patients who got the placebo and the patients who got the vaccine had basically the same rates of TB infection. And so it was, unfortunately, despite a measurable immune response, a clinical failure. As a result, there's been a lot of discussion about how to revise the sort of TB vaccine pipeline and what went wrong. And so there's a lot of emphasis on now not just relying on some alternative animal models, mice or guinea pigs, but to emphasize more the non-human primates and making sure we have an immune response in the non-human primates before moving on to the more expensive human trials, particularly phase 3 trials, although still that's certainly not a guarantee for success. So just a couple of concluding thoughts from our presentation. First is, despite small numbers of cases in the US, TB remains a significant cause of global public health morbidity and mortality. Although TB rates in the US and globally have declined, except for rates of MDR-TB, due to effective drugs developed during the 20th century, we are not on target to achieve the Millennium Development Goal of eradication by 2050. Infection is a spectrum from immune clearance of disease to latent, subclinical, and active disease, and the current diagnostic methods cannot differentiate between these states. Diagnostic methods currently include the PPD, the interferon gamma release assay, and the gene expert. And the treatment recommendations for latent and active disease have not changed significantly since 2000. Active research is ongoing to develop improved animal models for TB, better diagnostic methods, new drugs and drug regimens to shorten TB treatment duration, and more protective vaccines.
I just wanted to make sure we said thanks and we give a lot of acknowledgments to the people who make this possible. So this is not just NIH leadership, so this is Francis and this is my division director, Kathy, but this is the man who actually pays a lot of the bills for this and who's committed, who's an amazing guy and who's really committed his post-industrial career to making a difference in global health. And this is Bill Gates, right? You can sort of see that through the mask there. You can come and look at it on the screen, it's clearer. That's Bill Gates and Francis in our animal facility. Bill wanted to see the marmosets and actually came in and did a scan of a marmoset and came and saw the high throughput screening operation and spent a fair amount of time with us seeing how his money was spent. And I can't tell you how much admiration I have for this guy and what he's done for public health and for global health. There would be no big TB efforts if it was not for the Bill and Melinda Gates Foundation. So remember him then. Thanks.
Well, we have time for questions. Please use the microphone and we can pass it around. But while we're waiting, can I ask you a question? So when the Eskimos living all together in an igloo and they have tuberculosis, some people don't get tuberculosis. Why is that?
It's a good question. A lot of the, particularly the Inuits, have been studied quite closely for incidence of tuberculosis, and there has been there have been periods of dramatic change in the incidence. So they used to be very low frequency TB cases in Inuit populations. And it was only when they really started trading actively with North America and their diet changed from a high protein, high mostly seal meat and stuff they could get their hands on to something that was a much more typical Western diet, and they developed metabolic syndrome that we started to see a much higher incidence of TB. So there is a diet link.
Here's a group of people living all together under very adverse environmental circumstances. And my understanding is that within a given family, only some people get tuberculosis. The rest are still exposed to it and all, but what do they do?
So first of all, that's changed, but that doesn't erase the fact that there are people who are highly exposed that never develop disease. And this is one of the things that I think the immunology community in TB has become much more interested in understanding, why there are people who are apparently privileged in their TB susceptibility. That may be the key to understanding how to approach a vaccine in the future. Yep, that's an area of active research.
Do you have other fast-growing mycobacterial models for testing drugs, and specifically were you able to transfer these MDR and XDR mutations into other mycobacteria?
Yeah, that's been done. I mean, we don't like using the fast-growing organisms. I mean, the relationship between some of these environmental mycobacteria that grow quite quickly and M. tuberculosis itself is about as far as the fast-growing bacteria and E. coli are. So you do get very high false positive and false negative rates in using those in screening. So we don't do that a lot. The drug resistance mutations have been genetically moved very elegantly and understood in great detail for most of the drugs that are available.
What's the problem of the permeability of the granuloma or the cage necrosis? Some drugs must have more difficulty going through that. And does that, in your assay, does that involve typically the same lesions, or can you control that at all?
No, that's a very good question, and it's become it used to be very unappreciated, and I think it's much more appreciated these days that we have to pay attention to more than just the blood concentrations of drugs. We have to pay attention to drugs that can actually get into those poorly vascularized, highly necrotic lesions. So it is something we think about a lot in drug discovery today. We never thought about 10 years ago.
So my question is, I mean, for humans we have NIAID and Bill Gates who combat this, but how does this work for other mammals who are also highly susceptible to
Well, that's the strategy for when humans intervene in that, the strategy is usually we kill the animals, right? So in bovine TB, if you have an infected herd, they're usually culled. There's a huge controversy in the UK because the badgers present a natural reservoir of tuberculosis, and killing badgers has become something of a political firestorm in the UK to deal with it. So it's, when humans intervene, usually the animals suffer. I'd say that.
But they don't have like a different response rate to these kind of infections? I mean,
they don't, and there's pretty good evidence it's existed with other mammals as long as it's existed with humans. They live with the mortality.
Very nice presentations, I must say. Although I appreciate the difficulties treating this infection with all these drug trials going on, it's still surprising that isoniazid, this very, very old drug, is still the first line. I mean, also because I'm a hepatologist and I've seen people die from liver failure, and this is also a problem in prevalent areas like India, where although many die of tuberculosis, some die of liver failure.
This just isoniazid, rifampin, PZA, these drugs have been around for 40 years, and we are still using them, and they're still considered first line And people like Cliff just haven't been working hard enough to identify newer, better drugs. It's really the problem.
Guilty. I'll take that.
Stefan Jäger from the National Library of Medicine. We are running a screening program on chest X-ray over at our National Library. And we have a big database currently from Belarus with many multi-drug resistant X-rays. And for training our system, it's very important that we have the correct clinical data. But now it's still not clear to me what the gold standard is for diagnosing TB, given that I learned that there is NTB, meaning non-TB mycobacteria, and the gene expert might not be that reliable for pediatric cases. So I wonder, actually, if you want to determine 100% clinically that somebody has TB, what is the suggested procedure for doing this? And if it's possible at all.
There's no gold standard.
Really, you have to identify the organism from the patient to completely assuredly diagnose the infection. So for example, you have to identify the culture is really the best gold standard. Of course, sometimes it's not the best, because we do have culture negative TB, but it is hard to sometimes, especially in children, to get a sample that will yield a positive culture. So sometimes this is a problem that is still a big research issue, that the gene expert has been a test that is developed relatively recently, and there are second generation and even a third generation gene expert assays being developed. The second generation being able to diagnose not just rifampin resistance, but diagnose XDR resistance by identifying resistance to additional drugs. And the third generation is also to make the test 10 times more sensitive to TB than the first generation test. And so it'll be much, much, much more sensitive, and hopefully that will help with this problem with diagnosis. But yes, it is still an area of active researchers to develop better diagnostic methods.
So I know this has been an area of intense research, but I was wondering if you could comment quickly on what the state of the science is for predictive biomarkers for subclinical or latent infection going to active infection.
Yeah, so that's another whole seminar, right? I'd say that it's promising, right? I think there are some very promising things, candidate biomarkers, both immune and radiographic biomarkers that look very promising. There's been a lot of investments by a lot of big funding agencies to try to develop those biomarkers, and I would say there's nothing perfect. There's some very difficult issues, as was just referred to, with the sort of chicken and egg gold standard of what's a real, short of culture confirmation, what's a real TB case. But we're making progress in that area. That's still used all over the world. Yeah, it's one of the injectable second lines that's used in retreatment and in second line in MDR cases commonly.
No, I just want to say thank you. It was a great combine. You guys are great.
Thank you.
Really good. I just wonder if you could tell us a little bit more. I know in the late 90s, I have no idea about much of it after that, we had a lot of MDR here in the United States. I wonder if I would be able to deal away with it. It looks like we've been doing much better. But the MDR and the XDR, I wonder what is happening before tuberculosis, at least when I was a kid. I remember that the way we learned it was of those who are not, that are malnourished, those who live in chronic conditions. It's the same thing we see for MDR and XDR as well. And I wasn't surprised at all with the study that you talked about the vaccine, because that's where XDR, at least according to what you presented. So I was wondering, are they looking at other populations for vaccine, or at least looking at those type of TB to kind of include? Because I wasn't surprised so much when you say it wasn't too protected because of the area where we were studying and the TB that exists in those areas.
Yeah, in theory, ideally a TB vaccine would be protective no matter what the strain of TB, whether sensitive or resistant. So in theory, it shouldn't matter if you have XDR strain if the TB's vaccine works well. In terms of MDR and XDR rates in the US, yes, just like the drug-sensitive rates have declined, the rates of MDR and XDR are also really low. There's only been like 100 or so cases of MDR TB in the US per year, and XDR TB cases are probably 5 or less per year. So very low rates in the US. Of course, in the world, it's a completely different story.
And are we looking at anything other than treatment to deal with it? For example, some of the conditions of families or the individual, etc. Is there anything else you looked at other than developing medication?
There is, but those interventions aren't expected to have a big impact. I mean, but there were a couple of very large studies looking at sort of mass social strategies or mass behavioral strategies for impacting TB incidence, and they've been fairly disappointing in the results.
Since the TB mostly infect the lung, is there any like aerosol administration of the drugs to get higher concentration in like locally?
Yeah, it's been a hard sell. I mean, yes, people have talked about that. Yes, a couple of drugs have sort of gone into aerosol production and early clinical testing. It's generally, they're very old drugs, not very potent drugs, and the powder dose or the inhaled dose you have to give is generally large enough that it's caused problems with safety in early clinical trials. So there's not a lot of effort in that right now.